Hi, and welcome to another lesson in the physics video series. Today we are going to use vector analysis to solve the classic boat problem. Here we have a boat trying to go from one side of the river to the other side of the river while being pushed downstream. We're going to take a look at a few of the different vectors that come into play regarding its displacement and resultant velocities. Okay, let's get started. This problem is very similar to the crosswind of the airplane that we covered a few videos back. Here we have a boat starting at the dock, and it will be traveling across the river with a certain speed. Its speed will be VB, the boat speed. It's really a vector because it has a speed in this northward direction. Here's our compass rose. And it will go from one dock across the river's width to the other dock here. But while it is traveling across the river, in this case the northward direction, there is an eastward river speed pushing to the right. The boat has a combined motion of its own velocity plus the river's velocity. This is exactly like the crosswind of the airplane, except we're applying it to the boat. There are two triangles that you're going to see here. One is the physical displacement triangle. That's the actual distance from dock to dock and downstream, and the blue dashed line is the actual resultant displacement of the boat as it tries to cross the river. The smaller triangle is the velocity triangle. The boat velocity combined with the river velocity gives it this red dashed resultant, which is the resultant velocity of the boat plus the river. There are 5 basic concepts that are covered here. The first one is the time across the river. And we're going to learn that for this boat moving across the river, the time it takes, which comes from Formula 1 on the reference table, is time equals distance divided by speed. So that's the river width divided by the boat speed. We're going to do a problem, put some numbers in, and take a look at how this all works. Next, we want to find out how far downstream did the boat actually drift. The third question will be, what is the resultant speed of the boat? That's this red dashed resultant here, which is the combined boat speed and river speed. And we want to know what the resultant displacement and direction is, which is the blue dashed line. Here's a quick hint. You'll realize that the blue vector and the red vector are parallel to each other. That's because the resultant velocity is in the same direction as its displacement. And then we're going to talk about the course correction. If you did not want to be pushed downstream, but you wanted to make it straight across the river and get the passengers from this dock to that dock without having to make them walk all the way back upstream from where they were displaced. Here's a sample problem. Let's let the distance from dock to dock, the river's width, at this point be 100 meters. Let's say that the boat has a velocity of 8 meters per second north, and the river was pushing with a 5 meter second velocity east. Step 1. Let's find the time across the river. Well, we know that the time across the river is equal to the river width divided by the boat speed. The river width is in the y-axis, and the boat speed is also in the y-axis. So we just want the time. Time is never a vector. It's 100 meters. Divided by 8 meters per second gives us 12.5 seconds. This is a critical piece of information because whether you go straight across when there is no river speed, or whether you try to go straight across but the river pushes you downstream, it still takes 12.5 seconds to get there. Now the next question we're going to answer is, how far downstream does the river push the boat? Well, the boat is trying to go north, but the river is pushing eastward. So as the boat is crossing the river, it's being pushed eastward, which is why you have this blue diagonal resultant vector. So the x value, which is the downstream drift or downstream displacement, is equal to the river speed times the time across the river. Remember what I said earlier. No matter what, this boat will take 12.5 seconds to cross the river in a straight line along a 100-meter width at a speed of 8 meters per second. So x equals river speed times time, so it's the 5 meters per second times the time it takes to cross the river at 12.5 seconds, which gives you 62.5 meter downstream drift. So this boat, if it tries to go straight across while being pushed by the river, it winds up 62.5 meters away from the dock right here where it's trying to land. The next thing we're going to look at is the resultant velocity of the boat. First, we have to find the resultant speed, which is this red resultant vector right here. Since the boat is trying to cross the river at a speed of 8 meters per second while being pushed sideways, crosswind, in this case a cross flow of 5 meters per second, Pythagorize 5 squared plus 8 squared, you get 9.4 meters per second. So the boat picks up a little extra speed as it crosses the river because the other component of the velocity of the water pushes it just a little faster. Now think, if it was pushing in the same direction, the maximum it would be is 8 plus 5 meters per second. It would give you 13 meters per second if it was pushing as a tailwind, tail flow behind it. But it doesn't. It pushes on a 90-degree angle, which is orthogonal flow, and that gives you a little bit of a boost, which is the Pythagorean, and you get 9.4 meters per second. So it's going faster on the diagonal. Now this should make some sense because you're going to see this diagonal is longer than the 100 meters. So it would have to go a bit faster to cover a longer distance in the same 12.5 seconds. So how much longer is this blue dashed resultant vector of displacement? Well, it turns out to be the Pythagorean of the river's width plus the downstream distance. The river was 100 meters wide, and the downstream drift was 62.5. If you take the Pythagorean of that, you get 117.9. So it goes a little further. It goes 17 meters longer than it would have gone had it been able to go straight across without getting pushed downstream by the river. And so what's that angle of deviation right here? We're going to use the arctangent. In this case, I did the y over x, which gives me 57.9 degrees when I took the arctan of that ratio. The 57.9 degrees is really off of the x-axis, and that has to then be subtracted from 90 degrees, which gives us 32.1 degrees. The actual angle off the y-axis is 32.1 degrees, and the true angle off the x-axis is 57.9 degrees. You just have to see which angle is referenced in the question. Sometimes it's asked, what is the number of degrees off of the y-axis? And other times it's asked, what is the angle off of the horizontal or the x-axis? Let's do a small comparison between the red resultant velocity and its angle and the blue resultant displacement and its angle. As I mentioned earlier in this video, these two angles have to be the same. The displacement is the actual path that the boat takes. The velocity is the speed that the boat has on that path. So therefore, these two angles will be the same, 32.1 degrees. The red resultant is the speed in this direction. The blue resultant is the actual displacement in that same direction. And lastly, let's talk about course correction. Where would the pilot of the boat have to go in order to get straight across the other side and not have to make the passengers walk all the way upstream? Well, the answer is simple. The course correction is the negative of the angle. So he would point the boat upstream by the same number of degrees that it was being pushed downstream. So if he was being pushed off course by 32.1 degrees, he would have to head into the flow by 32.1 degrees. He would go this way. And then the river would push him back, and he would land exactly where he intended to land in the first place. So this is the vector analysis of the classic boat problem. Many students find this to be tricky, because you're dealing with two vector triangles. One is the displacement. That's the long blue resultant vector here. And the other is the velocity displacement. So you're dealing with two quantities at the same time. You're dealing with displacement and velocity. The angles of both are the same, but the actual magnitudes, the amount of the distance covered in displacement is a much larger number. This is the physical distance the boat traveled across the river. This is the speed triangle, and this is the speed the boat traveled in the direction of theta. That's what makes it a vector. And finally, the course correction. You have to go into the flow at the same angle you were pushed out of the flow. I hope you enjoyed this video, and I thank you for watching. This concludes our lesson on the vector analysis and the classic boat problem. I'll see you in the next video.